Welcome to the second part of the series on relativistic effects on a rotating frame. In the first part, we studied a rotating wheel from an outsider's perspective. We saw some pretty compelling general arguments that the circumference should become longer while the radius should stay the same. Such a discovery suggests that the spatial geometry, as experienced by someone living on a rotating disk, might not be Euclidean. Today, we look into that. Along the way, we encounter some intriguing challenges. Overcoming those challenges will teach us some valuable lessons about relativity and, in the end, reward us with the spatial metric of the rotating frame. How should we measure spatial distances in a rotating frame? Wait, what does space in space-time even mean in general? And how can this rotating space, whatever it means, be curved? After all, the geometry of space and time as a whole is flat. We need to go back to basics. Remember how distance and simultaneity are defined in the special theory of relativity, by sending light signals back and forth. If you're already familiar with the Einstein Syncronization, you may skip ahead. But not too far, for we will soon present a less known variant of it. The blue rocket on the left sends out a light signal to the purple rocket on the right, which receives it at event B, and immediately sends another light signal back. The blue rocket measures the time of the round trip, 2 times, say tau in this case. Then the blue rocket reasons as follows. Since the light always moves with the same speed c, distance between the 2 rockets must be c times the time of one-way light signal. And the time of the one-way light signal is assumed to be half the time of the round trip, tau in this case. Also, since the speed of light is assumed to be the same in both directions, it naturally makes sense for the blue rocket to say the event A, which is exactly halfway between its sending and receiving the signals, must have been simultaneous to the reflection event, B. In this manner, the blue rocket decides in hindsight, so to speak, which event along its world line must be synchronous with event B. The process very much relies on the assumption that the speed of light is isotropic, which means the same in all directions. As you may know, things get interesting if the 2 rockets are moving with respect to us. The situation then no longer appears symmetric to an outside observer. Us, the light paths seem to have different lengths and durations. It may therefore seem quite mistaken to assume the relative speed of light to be the same in both directions. Therefore, it might seem like a silly error to calculate distances based on the basic idea that distance traveled equals the duration times velocity. But that's exactly what we do in relativity. If we, like Einstein, truly believe the speed of light is constant, then we should trust this process. Feel free to contemplate on the rationality of such an assumption. We today simply take the leap and see what follows. For our purposes, what we need is a method for measuring distances. And please note how the distance between A and B is the proper time of a halfway trip times the speed of light. Usually the emphasis is on the synchronization and simultaneity. But indeed, if the light is assumed to have a universal speed, then when accompanied with a clock, it works as a natural measuring stick too. So that is our way of measuring distances in a rotating frame, or any frame for that matter. Light signal. First, let us facilitate the signal process a bit. The traditional way of sending a signal and waiting it to be reflected back is straightforward and works, but can be rather inefficient if we wish to find all the events simultaneous to a particular event located, say, at the origin. We therefore introduce a swift, if a bit theoretical version of the Einstein Syncronization. The observer sends out 2 time scouts along its world line, one to the future, one to the past, both equal separation in proper time tau. The one going to the future sends a light cone backwards in time. The one going to the past sends a light cone forwards in time. Those light cones will intersect and, being a conic section, will form some kind of an ellipse in space-time. The events along that ellipse are simultaneous to the original event at the origo, and they are all equidistant from the original event. The distance, denoted by the symbol sigma, is the proper time tau times the speed of light c, which in this picture is 1. It's quite easy to convince oneself by looking at the geometry that this is equivalent to the traditional Einstein synchronization. We're simply making the process more symmetric by sending signals both directions in time. The process works just as well with moving observers, where, as expected, it generates the usual tilted plane of simultaneous events. Indeed, this modified version of Einstein synchronization is quite easy to generalize to non-inertial world lines. For example, we could boldly apply it to a uniformly accelerated observer, aka Rindler observer. The world line of a Rindler observer is a hyperbola in space-time. When the Rindler observer sends out its time scouts and tracks the conic sections of their light cones, the resulting collection of simultaneous events looks like this. The coordinates obtained by this process are simply a rescaled version of the famous Rindler coordinates, where the light has a constant coordinate speed. The synchronization by light signals is often also called radar synchronization, because of its resemblance with the mechanism of a radar. The resulting coordinate system obtained with light cone intersections is sometimes called Märtzke Wheeler coordinates. The radar principle is clearly a generalization of the Einstein synchronization. It can in principle be used for any physical, subluminally moving observer to provide a coordinate system across the whole causally connected part of the spacetime, reference in the description. But how much sense will it make with non-inertial frames? There will be caveats, one of which will soon be pointed out, but the emergence of familiar Rindler coordinates gives hope that the radar construction might hold some value even beyond the safe old inertial frames. And in any case, it provides a geometrically attractive reformulation to the Einstein synchronization. Try to say that 3 times in a row as fast as you can. Let us therefore finally apply it to the rotating observer. The world line of a rotating observer is a twisting helicoid. Let us apply our radar process to it. To determine all the simultaneous events, the observer sends out 2 copies of itself, one into the past and another into the future. As these scouts propagate, they project out their respective light cones. We record the conic sections, which are again ellipses, and generate this interesting undulating surface. This surface is always space-like, and therefore it can safely be regarded as a surface of simultaneous events without fear of getting into a conflict with causality. This one surface is just one temporal slice, but as the time passes and the rocket follows its orbit, these respective surfaces of simultaneity will rotate with the rocket. Interesting. But does the undulating surface represent the spatial geometry of a rotating observer? Not quite. I mean, it can be useful for purposes where we only consider the point of view of a single observer. But for a more global description, it has at least one big problem. The process is not symmetric with respect to 2 observers. Let us explore this with simple light signals again. Consider a blue rocket at the center and a purple rocket orbiting the center at some radius. Let the blue rocket first gauge the distance by sending a beam to the purple rocket, which then reflects the signal back. The blue rocket records the time and decides, as before, that the distance between the rockets must be the travel time times the speed of light. However, now let the purple rocket try the same. It sends out a signal, the blue rocket at the center receives it and reflects the signal back. Curiously, although not essential to our argument, the return signal cannot trace back the original trajectory, but has to be directed into a new path. Also, if we were to observe this exchange of signals in a co-rotating frame, the trajectories of the beams would seem to bend. Anyway, as the purple rocket catches the return signal, it thinks the distance must be, as usual, the speed of light times... Wait a minute. The clock of the purple rocket has been running slow as compared to the center rocket, due to the time dilation since it's moving. Therefore, the purple rocket thinks the light has had less time to travel. Therefore, it thinks the distance, which is the radius of the orbit, is less than what the blue rocket thinks. So, in a rotating frame, two observers, if they use radar synchronization, might disagree about their relative distances. This goes to show why the radar synchronization has drawbacks in a global scale, at least for multiple observers. Yeah, too bad. But we had to give the radar construction a try, since it did seem like a promising candidate. And in fact, it still is. We just need one mathematical trick. This kind of failure to generalize a concept up to global scale is quite common in relativity. And what can we do? We localize. We divide the geometry into small, and by small we mean infinitesimal, pieces, and then patch those pieces back into a larger whole. A pretty standard move in relativity. So, here we now have a collection of rotating observers, aka Langevin observers, named after Paul Langevin, who was among the first to study the relativistic rotating frame. The idea is that each rocket is responsible for a small neighborhood around itself, tasked to determine its local geometry. Before we move on, note how the local frames of the Langevin observers, visualized by the arrows, are tilted. The tilting is according to a Lorentz transform corresponding to their instantaneous inertial frame. The local time axis tilts forward and the spatial axis tilts up. As they orbit, the instantaneous frames are rotating too. Unsurprisingly, the Langevin observers experience the world differently from a stationary observer, and also differently from each other, since the tilts are in different directions. Next, we switch to co-rotating coordinates, where the rockets are stationary. In the spacetime view, this has the effect of rectifying the helical world lines. Concurrently, the local axes of the Langevin observers tilt a second time. Now the time axis returns to its original vertical position, but the tangential space axis tilts even further up. In fact, the spatial axis may well tilt over 45 degrees. But the causality is safe, since the light cones are tilted as well. These co-rotating coordinates are called Born coordinates. We're ready to repeat the radar construction, but this time restricting to a small neighborhood around the rocket. We once again send out scout copies into the past and the future, but only to very near past and the very near future. They send out the light cones. As in the global case where we got that undulating surface, the light cones are translated along twisting world lines. The shifting into Born frame will skew the light cones. As a result, the light cones are no longer exactly cones, and therefore their intersection is no longer exactly an ellipse. This will create some curvature even in the infinitesimal limit of small separations. This, by the way, is the origin of the hyperbolic curvature in the spatial geometry, as we shall see. Here we see the difference before changing into co-rotating frame from two viewpoints. Side view brings forth the curvature. The top view emphasizes the tangential length contraction. For each individual co-rotating observer, the local experience is the same. The top view indicates what we might have expected from our earlier study of the Ehrenfest paradox. The tangential directions are contracted. The side view, on the other hand, exposes a rather troubling issue. These individual local patches, the spatial neighborhoods of different observers, are hard to compile into a global surface. I guess we could put a few of them together, but at the very least, after a full circle, we'd run into a gaping discontinuity. Observers on different sides of the discontinuity will disagree which event should be in the future and which event should be in the past. But we'll return to this issue after we've obtained the complete metric. Next, we will calculate the exact metric mathematically. Actually, for practice, let us first do this in the flat, non-rotating Minkowski metric. For simplicity, we drop the z-coordinate. Light always follows null paths, which in terms of a metric means proper interval ds equals 0. Which in turn implies this relation between time and spatial displacements. We can solve for dt to obtain two branches of solutions. The solution with the plus sign defines a future light cone, while the solution with the negative sign defines a past light cone. Now for the radar cone construction. First we pick a small epsilon, which will be a displacement in proper time. We sent out a scout copy into the past by 1 epsilon length along the world line. From there, it probes a light cone into its future. This cone is defined by the positive branch future cone equation, translated into the past by minus epsilon. Likewise, we send another scout into the future, again by equal epsilon length along the world line. The past cone is defined by the negative branch cone equation, translated into the future by plus epsilon. We find the intersection of these light cones by solving this system of two equations. Let us first solve in terms of the displacement epsilon. We get the following relation between the epsilon and the spatial displacements. Now remember, epsilon means the proper time of the one-way trip. Therefore, the distance of the one-way trip must be c times epsilon. We will take c to be 1, so epsilon is also equal to the distance. This means that the following combination, square root of dx squared plus dy squared, can be interpreted as the distance element of the spatial geometry, which happens to be exactly the Euclidean distance element. Good. If we, on the other hand, solve the dt from the light cone equations, we see that the light cones intersect when the time differential is 0, which means two events literally happen at the same time. So simultaneity in the Minkowski coordinates is exactly what we expect. The space of simultaneous events is simply the flat plane of a constant time coordinate. But things will change when we take the next step into the rotating frame. Okay, so let's do the same process starting with the Born chart. Wait. First we need the Born chart. We again drop the z-coordinate, since it plays no interesting role. 2 plus 1 flat metric can be represented in polar coordinates like this, where r is the distance from the center and theta is the polar angle. From here, it's easy to step into the co-rotating coordinates. We simply shift the angle variable theta according to the angular velocity omega. The coordinate differential changes accordingly. Only the angle variable theta is affected. Now we plug these into the polar metric and rearrange a bit, and it turns into the so-called Born metric. That's it. Also, recognize the factor in front of the time component. For simplicity, we can also set the speed of light to 1. It is the inverse of gamma factor in Lorentz transforms, which is always less than 1. Such a factor implies that the proper time runs slower than the coordinate time. Before we move on, let us examine what that ominous cross term dt times d theta does. What could such a combination entail? Here's an idea. Let us send light signals tangentially in opposite directions. We can set the radial differential to 0. Light follows null paths, so we set ds to be 0. And let us divide everything by dt squared. This is a quadratic equation, so we can solve it. Skipping the details, we get these two solutions. If we were to guide the light beams around closed circles, we could find that they complete the orbit in different periods, demonstrating the so-called Sagnac effect. We find that the speed of light depends on the direction, so clearly we're not in an inertial frame. Finally, we get to the prize. Again, we work out equations for the light cones in the Born metric. Light paths are defined by the null condition ds equals 0. This results in a second order equation for dt, which can be solved with the usual quadratic formula. The first root with the positive sign defines the future light cone, and the root with negative sign defines the past light cone. As before, we pick an epsilon for a displacement in proper time. Remember, it is according to the proper time, not coordinate time t, of the observer how the distance will be measured. This distinction plays a role now, since in Born coordinates the proper time runs slower than the coordinate time. So an epsilon step in proper time means gamma times epsilon step in the t-coordinate. Therefore, we need to shift the future cone into the past by minus gamma times epsilon, and the past cone into the future by plus gamma times epsilon. Right. So, the intersection of the cones defines the simultaneous moments and the spatial distance. From here on, we simply solve this pair of equations. Let us first solve for epsilon by subtracting the equations. With a little bit of algebraic manipulation, pause if you want to check the details, we obtain the following relation. It associates the proper time interval epsilon to the spatial coordinate differences of the light cone intersection. To reiterate the main argument, the proper time epsilon plays a double role in this equation. Epsilon is originally the proper time. On the other hand, the idea is to gauge the distance via the travel time of light signals. Now, on the left-hand side of the equation we have distance, while on the right-hand side we have a combination of spatial coordinate differentials. Thus we can, and will, interpret the right-hand side as the infinitesimal distance element of the spatial geometry. Done. Technical note, clearly this formula should be applied only in the region where the orbital velocity does not exceed the speed of light. This metric was first found by Paul Langevin, but the interpretation via light beam synchronization is due to Lev Landau and Evgeny Lifshitz. This Landau Lifshitz metric describes the geometry of a rotating frame. It is local, so to obtain the distance along some path, we have to integrate it. The construction itself is quite general and applies meaningfully even in curved spacetimes of general relativity, as long as the metric does not depend on the time coordinate. Reference in the description. Let us immediately test our new metric by calculating the distance around a circle of radius r. We parameterize a circular path c by the angle theta. Along the path, the radial coordinate is constant, so radial differential element drops. The constant factor comes out, leaving a trivial integral, and we find that, indeed, the circular path is longer than in Euclidean geometry by one gamma factor, where gamma depends on the tangential velocity. Similarly, it is easy to see that the radial distances are unaffected by the rotation. This all confirms what we found out when studying the Ehrenfest paradox in the previous video. But what about the spatial geometry of the rotating disk in general? Geodesics are, by definition, the straight lines or shortest paths in a Riemannian manifold. We do not solve the geodesic equation in this video, but we will draw what they look like. Here they grow out of some initial point as equidistant fronts. We can see it is slower to move tangentially than radially. Therefore, the shortest paths like to bend toward the center a bit. These geodesics are the shortest paths if one could move infinitely slow, thus unaffected by Coriolis-type forces. In particular, these are not the paths light rays would travel. Light moves with speed, and therefore has to experience the Coriolis-type forces. Also note this. Although light moves along the shortest path in space-time, it does not follow the shortest path in space. The fact that these geodesics clearly diverge from each other is also an indication that the spatial geometry in the rotating frame is hyperbolic. Nice. But we're still missing one half of the solution to the light cone sections. This time, let us solve for dt by adding the equations. We then obtain the following relation between coordinate time displacement and angular displacement. Let us rearrange a bit. In our practice example, the non-rotating frame, the corresponding equation was trivial. It simply stated that the dt had to be 0, which in turn meant that the surface of simultaneity is a flat plane. This time too, the equation defines nearby simultaneous events, but the relation is no longer trivial. We see that the slope between time coordinate and angular coordinate grows rapidly with radial coordinate r. We could try integrating and plotting this relation with respect to angle theta for various radial values. We might even venture to consider this surface. Could this surface represent the simultaneous event? Admittedly, the result looks pretty interesting, but there's an ugly discontinuity. We encountered this phenomenon earlier also. The issue clearly arises from the fact that each rocket thinks the next rocket in front of it is a bit in the future, and the rocket behind it is a bit in the past, so to speak. Now, locally this is not too bad. Relativistically pretty natural, in fact. But as we make a closed loop, we inevitably run into trouble. We must face the fact that there is simply no way of consistently synchronizing rotating observers around a closed loop, at least not in a way which locally reduces to the inertial frames of co-rotating observers. So no, better not interpret this surface as some space of synchronous events of the rotating frame. What are we to make of this? Is the whole enterprise, including Landau Lifshitz metric, in vain then? No. this is just relativity. There is no way to consistently define a global surface of simultaneity for a rotating frame, which locally reduces to the frames of co-rotating observers. But okay, so what? Global simultaneity is a rather fiddle concept anyways in relativity, and not having a precise concept of simultaneity does not necessarily prevent us from agreeing on a sensible concept of a space. You see, as long as two rockets stay stationary, and we are only talking about distance, the simultaneity does not really matter. The spatial distance can be a well-defined concept, even if time is not. But we are modifying the concept of space. It is not a slice of space-time, not a surface of simultaneous events. But it's not a new concept either. When you measure distances on a map, an ordinary map of the world for example, you care not about the time zones, which incidentally also have discontinuity. Still, it makes sense to talk about distances on a map. Likewise, in a rotating frame, we simply ignore the time coordinate. Like mathematical terms, take the geometric quotient. This is the kind of spatial space we can associate to a rotating frame. And this space is curved, hyperbolic to be more precise. To sum up this video, inspired by Einstein Syncronization, we decided to use light rays to measure distances. We reformulated the radar method into a more geometric version employing light cone intersections. It turned out, unfortunately, that the radar method was not suited for global distances. The winning idea was to apply the radar process only locally, and then integrate the local results into a global structure. Mathematically, this was performed with coordinate differentials to reach a metric clearly indicative of a hyperbolic geometry. The spatial space was noted to be a meaningful concept even if global clock synchronization was found to be impossible in the rotating frame. There's a lot more that could be said about rotating frames. The subject has produced plenty of discussion for over a century, and Einstein himself used the non-Euclidean nature of the rotating disk as an inspirational stepping stone to his general theory of relativity. This video was about geometry, but what about the actual experience in the rotating frame? What will an observer see in this frame where light travels along curved trajectories? In the next video, we will really try to step into the rotating disk and look around there. Focus is not on the technical aspects, but more on the visual effects. You can expect a lot of curved shapes. Thank you for watching. I hope you have a great day or a good night.